We recently explored the fascinating engineering that made the SR-71 possible, detailing its unique hybrid engines, coolant systems, and much more. But we neglected to explore one of the most fascinating aspects of its design: the new and exciting material science that made it possible. The SR-71's speed was not limited by the power of its engines. It was limited by the heat its structure could withstand. Today, we're going to explore titanium, a material that composed 93% of the SR-71's structure, a material that had never been truly utilized to its full potential until the SR-71 came along. We will explore its material properties, how it's made, and how the engineers of the SR-71 overcame the challenges they encountered while using the innovative new material. Titanium is one of those words that has entered common language. It's become synonymous with strength. SIA likens titanium to being bulletproof, and yes, with the right thickness, it is bulletproof. That's why it's used in the A-10 to protect the pilot. But in reality, the strongest titanium alloys are only about as strong as the strongest steel alloys, and their temperature tolerance is actually worse, while aluminium is lighter. What makes titanium special is not its tensile strength, weight, or high temperature performance, but a combination of all of these material properties that made it perfect for the SR-71. When choosing materials for a particular application, engineers will often consult something called a material selection diagram, where we plot two material properties on the X and Y axis. This allows us to see the relative benefits of materials so we can choose a material according to our needs. Here is a particularly relevant material selection diagram for the aerospace industry, with density on the x-axis and strength, the maximum pressure it can withstand before braking, on the y-axis. Our three primary metallic material choices for aircraft structures are aluminium, steel, and titanium, located here, here, and here. They spread across the y-axis because different alloys have different strengths. Steel is by far the heaviest, which rules it out of most aircraft structures, but it still gets used where its strength and heat tolerance is needed. We can also see that aluminium is in fact lighter than titanium, but titanium is stronger than aluminium. A better measure here is the strength to weight ratio, a ratio found by dividing the metal's strength by its density. After all, we can make an aluminium part stronger by just adding more material. But if we need to add so much material that the part is now heavier than an equivalent strength part made from titanium, then it's not worth it. Here, titanium wins. Its strength to weight ratio, or specific strength, is better than aluminium. Yet today, very little titanium is used in aviation. Planes primarily use aluminium, not titanium. Why is that? One reason: it's really expensive. Despite titanium being the 9th most common element in Earth's crust at a percent weight of 0.6%, there is more titanium in the Earth's crust than carbon, an element no one considers rare. Yet, in its purified form, it currently costs about $4,500 per metric ton. Aluminium, in comparison, costs a third of that at $1,500 per metric ton, which itself is a relatively expensive metal as a result of the high-energy electrolysis refinement process. To boot, that is today's price, which has dropped dramatically since the SR-71 was created. Titanium is expensive because its refinement process is a nightmare. To make titanium, we start with the feedstock in the form of titanium dioxide with this chemical formula. This oxide ore, called rutile, can be found in high concentrations in these dark, sandy soils. To build the SR-71, the US needed to buy vast quantities of the mineral from the Soviets, who had large deposits of rutile. To do this, they purchased the material through ghost organizations to hide the final destination of the material. Had the Soviets known what they were helping to build, they would not have sold that material. However, the US likely could have just purchased the material from mines in Australia. This is a relatively common raw material and is primarily used as a white pigment for paints, and is even found in sunscreen lotion as an ultraviolet radiation blocking pigment. Our trouble begins when we need to separate these two oxygen molecules to get pure titanium. For iron ore refinement, we heat it in the presence of carbon to force the oxygen to separate from the iron and bind to the carbon to form carbon dioxide. With aluminium oxide, its melting point is too high, so we instead dissolve it in a solvent and then use electrolysis to separate the oxygen molecule. Neither of these methods work with titanium. Titanium dioxide is both thermally stable and resistant to chemical attack. In the 1940s, the first reliable process to produce a chemically pure form of titanium was developed, called the Kroll process. This process made the SR-71 possible. It begins by first converting the titanium dioxide to titanium chloride. To do this, titanium dioxide is mixed with chlorine and pure carbon and heated. Any oxygen or nitrogen leaking in will ruin the process, so this has to be done in relatively small batches in a sealed vessel. Once this process is complete, we have titanium chloride. We then need to purify the titanium chloride from any impurities in the titanium ore through distillation, where we heat the product and separate titanium chloride using its lower boiling point. This titanium chloride vapor is fed into a stainless steel vessel containing molten magnesium at 1300 Kelvin. Titanium is highly reactive with oxygen at higher temperatures, so the vessel also needs to be sealed and filled with argon. Here, the titanium chloride reacts with the magnesium, which itself is an expensive metal, to form titanium and magnesium chloride. This reduction reaction is extremely slow, taking between 2 and 4 days. Then, once the reaction is complete, we need to let the product cool before removing the magnesium chloride products through high temperature distillation once again. The magnesium and chlorine are recycled with electrolysis, another energy intensive process. At this stage, we have titanium sponge, which needs further processing still. Typically, a porous metal like this would simply be heated and compressed into rolls of sheet metal or some other form of useful end product. But titanium, as we said, will react with oxygen and nitrogen if heated this high. We can't do that. So, the titanium sponge is compressed into an electrode along with any alloying metals needed. Heat is then generated through an electric arc current inside another sealed vessel. This form of heat needs no oxygen. This melts the electrode to form a large titanium ingot. This process results in an incredibly expensive material that becomes even more expensive as a result of the difficulty the engineers found when attempting to form it into its final shape. The engineers of the SR-71 were among the first people in history to make real use of the material. In that process, they ended up throwing away a lot of material, some through necessity, some through error. At times, the engineers were perplexed as what was causing problems, but thankfully, they documented and catalogued everything, which helped find trends in their failures. They discovered that spot-welded parts made in summer were failing very early in their life, but those welded in winter were fine. They eventually tracked the problem to the fact that the Burbank water treatment facility was adding chlorine to the water they used to clean the parts to prevent algae blooms in the summer, but took it out in winter. Chlorine, as we saw earlier, reacts with titanium, so they began using distilled water from this point on. They discovered that their cadmium-plated tools were leaving trace amounts of cadmium on the bolts, which would cause galvanic corrosion and cause the bolts to fail. This discovery led to all the cadmium tools being removed from the workshop. However, the largest wastes were caused by the lack of appropriate forging presses in the United States. Titanium alloys require much higher pressure to deform during forging than aluminium alloys or steel alloys. The best forge in the United States at the time could only produce 20% of the pressures needed to form these titanium parts. Clarence L. Johnson, the manager of Skunk Works at the time, pleaded for the development of an adequate forging press, which he stated would need to be a 250,000-ton metal forming press. Because of these inadequacies in forming capabilities, the final forging dimensions were nowhere near the design dimensions, and much of the forming process had to be completed through machining, meaning most of the material was cut away to form the part, resulting in 90% of the material going to waste. When your raw material costs this much, this kind of waste really hurts. To add insult to injury, Drill bits and other machining tools were being thrown away at a rapid pace. Titanium is a difficult material to machine, precisely because of its qualities that made it suitable for use in the SR-71. This is a material selection diagram with thermal conductivity on the x-axis and thermal expansion on the y-axis. Here we can see that titanium has low values for both, among the lowest for metals. Its low thermal expansion made accommodating thermal expansion as the plane heated up easier, but measures still had to be made to prevent it causing stress. The skin panels were fastened to the underlying structure with oblong holes, which would allow the skin to expand and contract without the fasteners causing buckling. And the skin over the wing was also corrugated to prevent warping during expansion. This is actually quite noticeable. You can see the sections that are corrugated quite clearly here. This didn't affect machining difficulties, but the extremely low thermal conductivity did. Machining metals produces a lot of heat that can damage the tool and cause unfavorable material properties in the titanium, like hardening, which means the metal under the fresh cut is now harder and therefore even more damaging to the tool. This is usually minimized with coolant, but titanium's low thermal conductivity means very little heat is transferred into the coolant. To deal with this, lower machining speeds need to be used, along with high volumes of coolant, which is also expensive. This slows the rate heat is generated and increases the rate it is removed. This slower machine speed makes the process incredibly slow, but this is offset by taking deeper cuts in each pass, which has the added benefit of cutting under the work-hardened layers. Titanium is also more sensitive to dull tools, as its stiffness is quite low. Machinists refer to metals like this as being gummy. They tend to form long chips that can clog the work area and cause all sorts of problems. If not properly managed, they can ruin the work surface and damage the tools. The engineers at Lockheed gradually learned these lessons and developed better tools for the job. When the first version of the SR-71 was being constructed, the drill bits used to cut the holes for the rivets could only drill 17 holes before they were unusable and needed to be discarded. By the end of the SR-71 program, they had developed a new drill bit that could drill 100 holes and then be sharpened for further use. By the end of the program, the engineers found enough improvements to save $19 million on the manufacturing program. It's pretty clear that titanium is expensive and extremely difficult to work with. Had aluminium been an option for the SR-71 with a little bit of added weight, the engineers would have jumped at the opportunity. But aluminium simply cannot deal with the temperatures that steel and titanium can. This is the material selection diagram displaying several metals' specific strength as a function of temperature. This is ultimately what made titanium so attractive for the SR-71. Titanium alloys maintain a great deal of their strength up to temperatures as high as 450 degrees Celsius. The same cannot be said for aluminium. What I find fascinating is that titanium's max operating temperature is less a function of loss in strength, but a function of oxidation. Pure titanium is highly reactive to oxygen, which forms an oxide layer on the outside of the metal, which is brittle. This oxide layer has some benefits as it provides excellent corrosion resistance, which is why many submarines use titanium to resist attack from salt water. But at higher temperatures, this oxide layer and titanium are soluble to oxygen, which means the oxygen can permeate through the outer oxide layer and diffuse into the metal, causing the oxide layer to grow and eventually helps dangerous cracks to form. The primary titanium alloy used in the SR-71 was 13% vanadium, 11% chromium, and 3% aluminium. Both chromium and aluminium form thermally stable oxide layers on the outer skin of the metal, which prevents oxygen from diffusing further into the metal and causing it to become even more brittle, which raises the max operating temperature of the metal, while the vanadium acts as a stabilizer for a crystal structure referred to as the beta phase, which leads to a material with higher tensile strength and better formability, with an ability to heat treat to a higher strength. In my humble opinion, advancements in material science like this have the largest knock-on effect in the advancement of human technologies. So much so that we name entire eras of human history after the materials we developed during that time. During World War II, the development of aluminium alloys suitable for aviation allowed for the emergence of some incredible planes and with that, some incredible tactics. Like aerial invasions, a method of invasion that first emerged in World War II, I just released the 5th episode of the Logistics of D-Day on Nebula, the streaming platform I created with my YouTube friends. In this episode, I explore the tactics of the Allied aerial landings in Normandy. I explore the technologies that helped the planes navigate to their drop zones in an era before GPS, where the airborne troops landed and why, and even explore some of the wooden gliders that were used to carry heavy equipment into the battlefield. I am currently working on the next episode, which explores the immense logistics required to build frontline airfields to facilitate close air support. The first episode of this series is available for free here on YouTube, if you'd like to see what you are signing up for. By signing up to Nebula, you will get access to future episodes and the 4 current exclusive episodes: How the Allies Fooled the Germans, which explores the deception tactics used to hide the location of the invasion; Clearing a Way to the Beaches, which explains the methods used to knock a hole through the walls of Fortress Europe; How the Allies Got Ashore, which explores the logistics of amphibious assault; and the latest episode, the logistics of the aerial landings. And to boot, you will get access to all Real Engineering videos with no ads. The best way to get access to Nebula is by signing up to CuriosityStream, which costs just $2.99 a month or $19.99 for an entire year. By doing that, you will get access to all of CuriosityStream's award-winning documentaries and get access to Nebula bundled with it for free. That's a great deal. CuriosityStream is all about big-budget, non-fiction videos, and we're building Nebula because we want a place for educational creators to try out new content ideas that might not work on YouTube, especially stuff that might get demonetized, like a war-related series. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering Real Engineering viewers free access to Nebula when you sign up at curiositystream.com/realengineering. As always, thanks for watching and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit and Discord server are below.